Hello and welcome back. The subject of this video will be static equilibrium. There are two conditions that must be satisfied in order for an object to be in static equilibrium. Remember, we have two different types of equilibrium. We can have dynamic equilibrium, in which the object is in motion, but it is not changing its state of motion. And then we can have static equilibrium, in which the object is not in motion, and of course not changing its state of motion as well. So the two conditions for static equilibrium are that the sum of all forces acting on the object must add to zero. And the second condition is the sum of all torques that are acting on an object must sum to zero. So we can have several different forces acting on an object, and for each force that is acting, we must calculate the resultant torque exerted by that force. And then each and every torque must be added together to see if that sum is zero or not. If the sum is not zero, then the object is not in static equilibrium. So let's look at an example of that using just a real easy scenario here, and that is a seesaw. So everybody has been on a seesaw sometime in their life, and these are the boards that are on a pivot point, and you place an adult and a child, let's say. So, or let's just represent this as two blocks, M1 and M2. So here's mass 1 and here is mass 2. Okay, so let's say that we know these distances relative to the axes as R1 and R2. So this is going to be R2, and this distance here will be R1, measured from the axes of rotation. Those are the distances. We'll be drawing vectors in a moment for them. And so what I'm going to do is take the board, which I'm going to consider the board to be massless. It's the most straightforward analysis. We include the mass as we layer on complexity onto the problem. I'm going to draw the board as just a line. And now I'm going to draw the forces acting. So there's a force being exerted by M1 that is down. Okay, and the force being exerted is the force of gravity. The Earth is pulling down on M1. The board feels that force because it's having to supply a normal force back up to keep it from falling. So this force is M1G. We have another force being exerted by M2, and that force is being exerted here. There's M2G. And then we have a force being exerted by the pivot point up, by the support that the board is laying on, and I'll just call that a normal force up. So there are the forces that are being exerted on this board. And now if I wanted to find out whether the board is in static equilibrium or not, then I would apply these equations. How do I apply them? Well, let's first of all look at the one that we are used to since chapter 4 applying, and that is the sum of the forces. So let's sum all the forces up. What forces do we have? Well, we have the normal force, and then we have these two forces of gravity. They are not in the same direction, but they all lie along a line, so we can use positives and negatives to keep track. So when we sum up all of the forces, we're going to have the normal force minus M1G minus M2G, those are both pointing downward, and we want that to be equal to 0 for static equilibrium. And then we also want the sum of the torques to be equal to 0. How do we sum up the torques? Well, we're going to sum up about the pivot point, which is this point right here. So I've drawn that as the dot right underneath the normal force being supplied by the pivot. And so we're going to draw these R1s and R2s as vectors. So here's vector R1 and here's vector R2. And I apologize if these are not identical. I just sort of sketched. But this R1 should be the same as that R1. This R2 should be the same as that R2. And actually, I should be a little bit careful. This R1 and R2 should be to the center of mass of these objects. So I'm actually going to erase this and fix it a little bit so that we have a little bit better representation between these two of R1 and R2. So we should have that go from there, and we should have this one go from here, so from the center of masses. So now how do we sum up the torques? Okay, so how many forces do I have acting about this pivot point? So this is my summing point for my torques. Okay, so notice that the normal force that's being supplied by the support itself is not any distance from my summing point. In other words, R is 0 for the normal force. So an R of 0 would be the magnitude part of the torque being exerted by this normal force is 0, so there is no torque being exerted by the normal force. The only torques being exerted about the axes of rotation are going to be due to these two masses, M1 and M2. So let's go ahead and use our standard coordinate system of into the board and out of the board, positive and negative z. So let's say that out of the board is going to be positive z hat, and into the board is going to be negative z hat. So let's look at this first torque. So we're going to have R1 crossed into M1G. That's going to give me a torque that is out of the board, so that's going to be a positive z. So the magnitude of the first vector, magnitude of the second the second vector is the force m1g times the sine of the angle in between the vector r1 and m1g, and that is 90 degrees. And then the direction is z hat. So there's the torque exerted by the first vector. The torque exerted by the second vector, well, let's get the direction part. R crossed into the force is going to give me a force into the board, so that's minus z hat. The magnitude part is going to be the magnitude of the first vector, R2, magnitude of the force, sine of the angle in between R and F, and that's again 90 degrees, and that's in the minus z hat direction. And in order for us to have static equilibrium, this sum has to be 0. So again, this is for static equilibrium. Okay? In this particular case, we only had 3 forces acting. Notice that if I know M1, if I know 3 of these 4, I can solve for the fourth one using this equation, and then I can come back and figure out what the normal force is. If I already know M1 and M2, I can immediately get the normal force, but then I need either R1 or R2 to be able to solve for the other variable. So these are the 2 equations that we can use to solve for unknown quantities when we apply the conditions for static equilibrium to a seesaw scenario. And remember, this is normally like 2 people, maybe a child and an adult. And imagine if it is a child and adult, which one would be M1 and which one would be M2 for us to have static equilibrium on this board? Would M1 be the child, or would M1 be the adult? So you think about that, and then the next video we're going to actually work some problems from the back of the text, applying the conditions for static equilibrium to some more complicated problems, and hopefully you can readily see which has to be the adult and which has to be the child. And if not, we should talk about it. We'll see you next time.